Hello. In this notebook, I am demonstrating the TensorFlow functional API version of basic neural network for nonlinear regression. So, the goal of this notebook is to build a three hidden layer neural network that learns a nonlinear relationship between three input variables and one continuous output. Okay. From the first cell, uh, we'll actually install all the required libraries, TensorFlow, scikit-learn, and Matplot libraries. And then the TensorFlow is used for building and training the model. Scikit-learn is used for splitting the dataset and PCA, and Matplot library is used for data and result visualization. Next, in this section, I import NumPy, Matplot library and the required scikit-learn, and I set a random seed so that the dataset and results are reproducible. Then I define a function called makeData. This function creates a synthetic nonlinear regression data by first generating x1 from a uniform range, x2 from another uniform range, and x3 from another uniform range. Then it computes target y using the nonlinear equation. The equation contains a sine term, quadratic term, and a cubic term, as we can see here, and interaction terms between these variables. So this is not a simple linear regression problem. It has nonlinear structure, which makes it a good fit for neural network. Next, I combine these three variables into a future matrix X and reshape Y into a column vector. After generating the full dataset, I split into a training dataset, validation set, and test set. The training set is used to learn the model parameters. The validation set is used to monitor generalization during training, and the test set is used for only final evaluation. Finally, I print the shape of all these three tests to verify the split to correction. In this cell, I create a 4D style plot of the synthetic dataset. Since the problem has three input variables and one output variable, it can be four dimensional. Because we cannot directly visualize all four dimensions at once, I use a PCA to reduce the three input features into principal components. Then I plot a three PCA component into a 3D space. To represent the fourth dimension, which is the target Y, to represent a four dimension which is target y, I use color, so that x-axis is PCA1 and y-axis is PCA2 and z-axis is PCA3, and the color bar shows the value of y. This gives a compact way to visualize the nonlinear structure of the dataset. Next is TensorFlow functional API. This is the main building model building section. First, I import a TensorFlow and then set the TensorFlow random seed. Then I define the neural network using the functional API. I start by creating a input layer, which is tf.keras.input with a shape 3 and name feature. This means each sample has a 3 features. Then I add these 3 hidden dense layers. First hidden layer with a 32 neurons and ReLU activation, second one with 24 neurons and ReLU activation, third with 16 neurons and ReLU activation. Finally, I define the output layer with one neuron, since this is a regression task and the output is a single continuous value. After that, I create the model by explicitly connecting the input tensor to the output tensor here, and connecting from input tensor to output tensor. This is why it is called the function, like a functional API. The graph is defined by layer, input to output. Then I compile the model using Adam optimizer with a learning rate of 0.01, and then mean squared error as the square loss function, and mean absolute error as additional metric. Finally, I call model.summary to display the architecture and the parameters. So now we can say the output layer by layer is displayed with the output and its shape and also the parameters. So Yeah, it also says total trainable parameters and non-trainable parameters along with the size mentioned here. In this cell, I train the model using model.fit and I pass xtrain, ytrain as the training data and xval, yval as the validation data. The model is trained for 250 epochs with batch size of 64 and I set the verbose to 0 to keep the notebook output neat. The result is stored in the history object which tracks how the training loss and validation loss change over time. At end, I print training is complete. Next, in this section, I visualize a loss curve. I plot training loss and validation loss, as we can see, across all epochs. This helps me understand whether the model is learning properly. If both losses go down and remain reasonably close, it suggests the model is learning well and generalizing properly. This plot is very important because it shows the behavior of the network during training, not just a final output. In this cell, I define a helper function called regression report, and this function calculates several important regression evaluation metrics, which is mean squared error, root mean squared error, or mean absolute error, and R squared, which means how well the R square as in how well the model explains the variance in the target. This helper makes the final evaluation section cleaner and easier to interpret. And in the last section, I use a trained model to predict the test set. The prediction are stored in the y-test spread. Then I call the regression report function to print the final regression metric for the TensorFlow functional API network. These values show how well the model performs on unseen test data. After that, I create a scatter plot of a true target value and target value on one axis and the predicted target, which is like y, on the other axis. If the model is performing really well, the point should cluster to the ideal diagonal relationship. So this plot gives a visual confirmation of prediction quality. So yeah, that's it with this notebook demo. Thank you.